All right, now in this video, we're going to jump into our section 3.4. It deals all about with radioactivity, what it means for an element to be radioactive. We've talked a lot about nuclear chemistry and radioactive wastes that are created in nuclear reactors. So let's actually talk about what that radioactivity is all about. So in this section, the vocabulary we'll be going over and that you'll be familiar with by the end of this video, it's radiation, radioactive, stability, alpha particle, beta particle, gamma ray, radioactive decay, and half-life. All right, so first let's start off talking about what stability is. When we're talking about the stability of an element or the stability of a nucleus, what is that we're really talking about? So if you remember from the section 3.2 that we had on the structure of an atom, you know that all atoms are made of just these three pieces. We have the protons in orange and neutrons in gray. They're both located in the nucleus of the atom, and we have the electrons in the area surrounding the nucleus. So for this, we're just going to focus on the protons and the neutrons. We want to focus on the nucleus of the atom. Now remember that nucleus is always held together by the strong nuclear force, right? And so when we're talking about nuclear reactions, we've talked about nuclear reactors, the energy that gets released, that's the energy of the strong nuclear force. So we're breaking up our nuclei of atoms and we're releasing the strong nuclear force. Now, this strong nuclear force, again, this is everything that holds our atoms together, and everything is made, or all matter is made of atoms. So this strong nuclear force, it plays a very important role, but it's actually a very careful balancing act between protons and neutrons. And so if I pull up our simulation, the atom builder that we had last week, and so I can build different atoms, and one of these options that I have on here is that I can choose if my atoms will be stable or unstable. And it all comes down to the balance they have between protons and neutrons. So if I just start building my atoms and pull up a neutron, sorry, no, that's a proton in the nucleus, we can see that I have a stable nucleus, right? So, but if I were to add two protons on this, notice that it goes into unstable just as soon as I add one proton. So in this case, I don't have enough neutrons to help balance out my strong nuclear force. Now, if I were to just add one neutron, you see that it went from being unstable to being stable. So I can mess with that. I have two protons and zero neutrons. It is unstable. As soon as I drop in that neutron, it becomes stable. So again, I can keep adding more. If I add two neutrons, it's still stable. But notice that when I add that third neutron, it becomes unstable again. So again, this is out of balance. And so I would have to add yet another proton to make this stable if I had three neutrons. And I could keep adding more neutrons, still stable. If I add neutron number 5, it becomes unstable again. So you can see I have a lot more neutrons here than you have protons. And for knowing when your atom will be stable or unstable based on the number of protons and neutrons, it's not as simple as saying as, if you have 3 protons, you would need 3 neutrons. No, there's a lot of math that goes into it. And to be honest, it's actually really difficult to calculate. So we won't go too much into detail for that, but you should just know that for stable nuclei, you need a careful balance between your protons and neutrons, and that it's not always a one-to-one balance. All right, but now getting back to this, we know that the strong nuclear force, it's a balance between protons and neutrons, so it matters how much of each you have. It's difficult to predict, so we won't be predicting it, but we just need to understand what those are. All right, so now when you have that strong nuclear force and it's balanced, then you can call that atom to be stable. We saw that in the simulation a little bit. And so this gives the atom a state of low energy. That means, and it's not going to change unless there's a very good reason for it. And then when the strong nuclear force is not balanced, either you have too many or too few neutrons to go with your protons, then we can call that atom to be unstable. This is when you saw in the simulation that my atom was shaking. It's unstable because it has too much energy and it doesn't know what to do with that. And a lot of these atoms, they want to get rid of that extra amount of the strong nuclear force. Now, this would be what we'd call a state of high energy. And so if you can think of it this way, Instead, imagine doing a handstand and how it compares to just either sitting in a chair or standing on your feet. You know that standing on your feet and sitting on a chair, they're two activities that don't require a lot of energy. And you could stand or sit for hours and you'd be totally fine for it. But if you try to get into a handstand, this is a lot more difficult to keep it up. And so you'd probably lose your balance after a few seconds or a few minutes if you're really good at handstands. And so the reason that you would lose your balance in a handstand or you'd fall over is because you have too much energy and you can't keep up with the demands of that energy. And so you would lose your balance, you would fall to the floor, and once you're on the floor, you're in a state of a lot less energy. You're in a state of low energy. And so if you're laying on the ground, if it's comfortable for you, then you'd need a good reason to get up from that. All right, and just like you can't hold a handstand for more than a couple of minutes, these atoms that have an unbalanced strong nuclear force in their nuclei, they want to be able to come to a low energy. They want to get rid of that excess energy that they have that's out of balance and get into a position that's a lot more comfortable. All right, and so that's just a normal tendency of nature. And so it's actually the second law of thermodynamics. We won't get too much into it, but if you want to simplify that law of thermodynamics, you could just say that things that are very unstable, they want to become stable. They want to lose a lot of energy and have the least amount that they need to hold. All right, so when atoms do this, they emit radiation. So when we're talking about nuclear activity, and we're talking about radiation of certain types of matter, say they're radioactive. And so when they release a lot of that excess energy, that's what we measure as radiation. And so now these releases of the energy, they can come through as either as subatomic particles that carry that energy or as electromagnetic waves. So it might be different types of light and waves, energy waves that we can measure. And so when atoms go through this and they emit the radiation, we just say that they're radioactive. All right, and when we're talking about radiation, we have to know that there's actually different types of radiation, and they all do different things. They work in different ways. So let's go ahead and look at the different types of radiation and see what the differences between them are. All right, so our different types of radiation, they each have unique properties that we can use to separate them out and know how to deal with them in different ways. So our three types that we'll focus on is the alpha radiation, beta radiation, and gamma radiation, or you might also call them alpha particles, beta particles, and then gamma rays. Notice that gamma, that's the one that's different. I'll let you know why in just seconds, but we'll look at three of their properties. So we are looking at the mass of each of these, what their charge will be, and what type of energy or how much energy they can each carry. Now, I'll start with alpha. It's named after the Greek letter alpha in the Greek alphabet. All right, and the mass that it carries, it's basically just two protons and two neutrons. So this will be very similar to an atom of helium. But for its mass, we just measured 4 atomic mass units for it. Will carry a positive charge because it has two protons. This is where it gets its positive charge. The neutrons, they don't carry a charge, so they don't add to the charge of the protons. They also they don't cancel in any way either. And energy, just speaking in relative terms, we don't need to know a number that goes with it. We just need to know that alpha particles are the weakest type of radiation that we can have. They carry the least amount of energy of these three that we're seeing. Next up, we have the beta radiation or beta particles. And these are essentially just a single electron. Now, because they're electrons, if you remember from our atomic structure, you remember that electrons are negative, and so beta particles in the same way, they carry a negative charge. And these beta particles, they will carry a little bit more energy than your alpha particles, and so we'll consider them to be medium strength type of radiation. And finally, we have the gamma rays. Now, these are not particles because they don't carry any mass. They are just pure packets of energy, and they're usually seen in an electromagnetic wave. and we'll see more of those in the next section where we start talking about electrons. But you know, getting sidetracked here, the charge of it, like, because it doesn't have any protons and it doesn't have any electrons, the charge of a gamma ray will be neutral, and this is the highest type, or it carries the most amount of energy out of our three types of radiation. So gamma rays are actually really harmful, and a very common source of gamma rays are exploding stars. So if you can imagine how much energy is being released when stars go supernova, far off in the galaxy, they're releasing gamma rays, and this is how strong these gamma rays are. All right, and so just we can have different protections against these different types of particles, and it's all based on how much energy they carry, how strong they are. So alpha particles, I told you, they're very relatively weak, and they can be stopped by just a sheet of paper. It doesn't take much to stop alpha particles. And beta particles, they're a little bit stronger, so they can fly right through that sheet of paper, and so it takes a little bit more sturdy to stop beta particles. In this example, we have just a small sheet of aluminum, and then but also a lot of your clothes that you wear, cotton and all those types of fibers, they're usually thick enough to stop beta particles as well. And like I said, gamma rays are the strongest. They have the most potential to do the most damage because they tear right through all those protections that would stop a beta particle. So the clothes that you wear, they don't offer you any protection against gamma rays. And so you can see how this is a really thick block of lead that it takes to stop the gamma rays. So maybe if you ever had to take X-rays, usually they make you put on a vest that is made of lead, and so that's to protect the rest of your body from those high energy beams of X-rays that they're using. Now, what we talked about is that when we have atoms that are unstable, they can become stable when they emit radiation. And just to have a visual of what that might look like is that think if you have a single atom of uranium on here. We have a uranium atom, and if it goes through alpha decay, that means that it will lose an alpha particle looks like this. It will have two protons and two neutrons. Then the nucleus, the large nucleus, will look a lot more like this. Notice that it will be a new element, so we're making thorium out of our uranium when we get rid of an alpha particle. Notice that they have a different number of protons, so we go from 92 in uranium to 90 in thorium, and this is what makes it a new element because we're changing the amount of protons we have in the nucleus. So now, you might wonder how quickly this can happen. How many times this happened to an atom, and so we can actually calculate all that using what is called the half-life. This is the rate at which an element will go from being unstable to being stable. So you can also think of it as how long or how much time will pass before 50% or one half of your sample becomes stable. All right, and if you were to take all that information of how long you have an unstable atom, and then over time, when it becomes a different atom, you could plot this in a graph and it would look something like this. Notice that you start at a very high point on your graph and it quickly drops off. You lower down very quickly, and then the rate starts to slow down. Right, it starts to plateau out, and you have a lot less change over the same amount of time. So it's an example of an exponential function. Maybe you've seen these in Algebra 1. You've definitely seen these in Algebra 2. So now there's a formula we can use for calculating the half-lives. We won't get into too deeply for it today, but I just want to show you this example so it can start to make sense a little bit more. So let's say that theoretically we just had some element X. It doesn't really matter what this is, but we just want to know that we started with 100 grams of that element X. And we know that the half-life of our element X is 10 days. So it means that every 10 days, we'll have half the amount that we started with. So if our initial amount is 100 grams, this is what we started with on day 1, minute 0. This is where we start. After exactly 10 days will pass, and what we have left of our sample, we have 50 grams. We have 50% of it. The other half has decayed away into something that is more stable, a different type of element. Then, if another 10 days go back, our new amount that we have left will be 25% of what we started with, but this is also half of what we had at one stage before. So if we start with 100 grams, after 10 days, we have 50 grams left. And then after 10 more days, we have half of 50. So we'll have 25 left. We can keep this going all along. If we wait 10 more days, we'll have half of 25, which becomes 12 grams of the 100 that we started with. And after 10 more days, again, we'll take half of 12 and we'll have 6. We can keep going until we run out of stuff to measure. So again, if we have 6 grams in this, we wait 10 more days, another half-life, then we will be left with half of 6. We'll have 3 grams, and this will always keep going. It'll slow down at every pace, but we will always be taking just half of what we had in the stage before. All right, and that wraps up with what we're talking about here in radioactivity. We'll have a short lab to go with this, especially with a half-life, because I think it can be one of those concepts that doesn't really make sense the first time, and it's really useful to get some more hands-on experience. So make sure you're ready for that lab. Grab the supplies whenever you're ready, and if you run into any problems, make sure you let me know so that I can help you through it.